Right, we are beginning our discussion now, focusing on what we call the vertical projectile motion. And that is the subject of the discussion at the moment. We're looking at question 3 that came in the June 2023 paper. And in this particular question, we are looking at parts that remain extremely important in terms of what happens when objects are thrown into the air, right, either vertically upwards or vertically downwards. And we try to make sense of that. So let's see what we have here. Ball A is dropped from rest from the top of a building, 15.2 meters high. So we drop A from the top of the building. Here is the building that is 15.2 meters high. And from the roof, A is released. Okay, but also the words that the examiner uses are very important. So it is dropped and it is not thrown, because if it is dropped, then it's not given an initial velocity. Okay, so it's just let go. Somebody lets it go. But once again, from rest. So it was not moving. The choice of words of the examiner is very, very cautious here, because they're looking at the fact that it is dropped from rest from the top of a building 15.2 meters high. After ball A has fallen 3.2 meters, the second ball is projected vertically upwards from the ground. Okay, after A has fallen 3.2 meters. So let's see, after A has gone down, that just 3.2 meters, another ball is thrown up. Okay, let's see what's happening over here. After ball A has fallen 3.2 meters, the second ball is projected vertically upwards from the ground. After a while, the two balls strike the ground at the same time. Okay. After ball A has fallen 3.2 meters, a second ball is projected vertically upwards. Okay. And when this is happening, right, when this is happening, something interesting is okay. So these two balls are moving in different directions. A has fallen 3.2 meters, a second ball B is projected vertically upwards from the ground. So one is going down by 3.2 meters on its way down. Obviously, the height measured from the position of release, and B is thrown up. Okay, so B is projected vertically upwards, so B is like thrown. After a while, the two balls strike the ground at the same time. Who? After a while, these two balls hit the ground simultaneously. Okay, this one goes down, A goes down, B goes up, but they strike the ground at the same time. How magical is that? B is thrown up, A is released from rest, but they happen to hit the ground at the same time. Define the term free fall. Okay, nice question these, but it's a very, very interesting one, because we're looking at the what is happening here. And what is the solution to this? 3 um 3.1 solution. Okay, so right, you continue, please. So we need to define the term free fall. What is free fall? Might have seen that, but we're discussing here, so we try and discuss together so that we agree on sort of what is the standard definition of this. So define the term free fall. What does free fall mean? Right, free fall means motion, motion under the influence. under the influence of gravity. Under the influence of gravity only. What does free fall mean? It means motion under the influence of gravity only, and that is what we have. And that is free fall. Next question. Right, so the next question is question 3.2. Right, here comes question 3.2. Calculate the time taken for ball A to strike the ground. The magnitude of the velocity with which ball A, with which ball B was projected from the ground. Right, so the marks for these questions are as follows. So the free fall question, 2 marks. Define the term free fall, motion under the influence of gravity only. And then now there is this one of 3.2.1 is 3 marks. And this one is exactly 5 marks. Right, so calculate the time taken for ball A to strike the ground. So we're asking the question, how much time did it take for ball A to actually strike the ground? And that is extremely important. Right. So to look at that one, 3.2.1, let's just do it quickly. Right, so in 3.2.1, you need to make a choice. Choose upwards as positive. So which means delta y is equal to vi delta t plus 1/2 a delta t squared. Okay. So if you choose upwards as positive, so we can write down the data. Right, so the couple of things we want the time taken, so we are saying sort of delta t is a question mark. We know the acceleration A is obviously is acceleration due to gravity, because this is a projectile, so but it's going down. So the acceleration is always downwards for something going down. And because it is therefore because it is downwards is therefore negative. Okay. Delta y now is the next thing. The delta y now is 15.2 meters, but in which direction is a 15.2? Is it upwards or is it downwards? So you need to think of that one. So, but merely looking at this question, you actually can realize that it is the ball itself. Ball A is dropped from upwards and is going down, and therefore it is a negative displacement of, because height itself is a displacement. Okay, like so. Right, and then what do we need? We need the time. Okay, so let's just check here. What is the initial velocity? Because it was dropped, and therefore the initial velocity is 0 meters per second. So the change is minus 15.2. 0 into delta t. That is what we want, 1 delta t. Plus 1/2 of the acceleration, which is due to gravity straight down, just leaving the units out. And then we have delta t squared. Oops. Right, so we continue now with this question. So this is delta t squared. Right, so this is 0, then so that we have minus 15.2, which is that one, 9.8, divided by 2. Use a calculator to say 9.8 divided by 2. What is it? It's minus 4.9 using a calculator. Delta t squared. Right, we're looking for the time now, so we perform division. So therefore we have minus 15.2, which is minus 4.9 delta t squared. You divide by minus 4.9 minus 4.9. Right. So 15.2 divided by 4.9, which is delta t squared is actually 3.10204.08163. Right, and then we are interested in, okay, this one is still the solution to 3.2.1. So it is 3.2.1, so that we have delta t squared, you take the square root here. Okay, so you have this here, which is 3.10204.08163. What is delta t? Let's see what we get here. Right, so we're continuing to solve. Want to get the square root here. Let's just get the square root quickly. So it is the square root of 3.1, 02, 04, 081, 63.
It's 1,76126.
Okay, well done. That's the correct answer. Okay, you got about 1.7613 approximately, okay, seconds. So which means approximately 1.76 seconds. Now we're interested in doing the next question. What is the next question? So to do this question, let's just go through this and make sure you understand what's happening. Right, remember it was thrown from the top of a building of this height, delta y, because we're looking at vertical motion. We're looking at delta y. Horizontal motion would therefore be delta x. Right, it's vertical motion, and therefore we have that, we have the a there, which is minus 9.8. And we have therefore that the initial velocity, because it was dropped, it was 0, so it was just released from the top of the building, and therefore it started accelerating because it became a projectile at this velocity, this acceleration of minus 9.8 meters per second squared, please. Right, because it's acceleration, and therefore you have delta t squared, and you have minus 15.2, etc. And now you just solved here accordingly. Okay, you just think of these and make sure you understand these. The next point, please. Right, 3.2.2, the magnitude of the velocity with which ball B was projected from the ground. At what velocity was this ball B thrown up? This one, that's the question. How fast was it moving when it was projected straight up? How fast was it moving? So what was the initial velocity of this ball? Okay. So this is very, very interesting. Just look at the answer to this. 3.2.2. Right, so 3.2.2. So we are choosing upwards. As positive. Right, so if you choose upward as positive, what happens? One way to do this question is to then say, we're going to look at the amount of time taken by ball A. Delta y is VI delta t plus 1/2 A delta t squared. So we're looking for the amount of time that ball A took to cover the 3.2 meters. In which case, it's going to be, because it's straight down and we're choosing upwards as positive, so down is negative. So it's going to be minus 3.2. Then because it was dropped, initial velocity is 0. The change in time is there. 1/2. All right, so if you had to write down some data, you realize therefore that delta y is minus 3.2 meters. VI is 0. A is minus 9.8 meters per second squared. Okay, so minus. Minus 9.8. And then We have delta t squared. We're looking at the amount of time that ball A took. So delta t is a question mark. Right, delta t is a question mark. So the amount of time it took. So now at this point, we'd have this, which is minus 3.2, which equals minus 4.9 delta t squared. So you then take the minus 3.2 minus 4.9 delta t squared. You divide by minus 4.9. You divide by minus 4.9, which means delta t squared is something here. Right. So you continue, please, but need to use our calculator. What is 3.2 divided by?
It's 0.65.
Okay, 0.65, eh?
Yeah.
Yeah, good, well done. Right, 0.653 thereabout. So we're still looking at 3.2.2. So you got 0.65. Zero 0.65 delta t. So now if you look at the 0.65, then you take the square root of that. What do you get, Lerato?
It's 0.0880. No, 0.81.
Okay, that's fine. 0.8, like 0.6, right?
Yeah.
Okay, that's fine. Seconds. So let's just check this one here. Yeah, which is about 0.81 seconds is delta t. Okay, the meaning of this is that A is going to take, ball A is going to take this amount of time to cover this this particular displacement, this particular height. But then it means therefore that what is the total time in the beginning here? 1.76. So you need to find, we want to know for how long will B be in flight. So for how long will B be in the air? So we're looking at 3.2.2. The change in time for B, which is 1.76 minus 0.81, which is 0.95 seconds. Meaning B is going to be in flight for this much.
Mm.
It's going to be in the air for this much. It's going to be a projectile for that much. So if B is going to be in flight for that much, at what velocity was B thrown if this is the amount of time B took in flight? But also, the couple of things to understand. So we're going to use delta Y equals VI delta T plus 1/2 A delta T squared. Okay, right, 0 delta T plus 1/2. Okay, So we understand therefore that B was thrown up and therefore its acceleration was just positive. Okay, but it's something we know the amount of time. We know that B is going to be in flight for 0.95 seconds. Which is 0.95 squared. Okay, we chose upward as positive, and therefore it's going to go up and then come down. B is going to go up, but it's going to come back down again. But its initial velocity is what we want. Excuse. We want the initial velocity. Okay, let's see, analyze this. All right, so we are really saying because it's going to come back down, so the displacement is going to be 0. It's going to come back to the ground. So in physics, if you go like this and you go back like this, what displacement have you covered? You went up and then you came back down. We're going back to the same position, so the displacement is going to be 0 for B. Now, the initial velocity that we just projected is understood. The time taken is 0.95. That's half into minus 9.8, 0.95 squared.
The answer is negative 3.47225.
Okay, let's just see what that is. Right, so at this point, then you can take these things and like move them to the other side and divide by these. So because this one is already negative, so you can look at this as 1/2 0.9598 0.95 squared 0.95. Okay, so what this means is let's just do that. What answer do we get there? Just finish that off. Yeah, it needs a calculator. So, okay, because this one was negative, but now if you move it across, it's going to be positive and divide by 0.95. So what we're having is 0.5 times 0.98 times 0.95 times 0.95, and then divide by 0.95. Check what you're getting. Right, you're getting 0.4655.
Yes.
0.4655 meters per second. So that means that in 3.2.2, zero point 4655. Okay. Approximately 0.466 meters per second. Okay, so yeah, let's just see that. Next point. Next question. On the same system of axis, 3.3. On the same. System of axis, draw. Position. Time graphs. Goodness me. Time graphs to show the motions of both ball A and ball B. From the instant ball A is dropped, right is dropped until the time it reaches the ground. Take the ground is the 0 position. In 3.3, label the graphs. A and B. Clearly indicate the following on the graphs. The starting, time for each ball, position 2, the initial position, right, the initial position, position of each ball, the time when the balls strike the ground. Oops. Okay, strike the ground. Okay, soar. Right, so let's continue. Right, on the same system of axes, draw position time graphs to show the motions of both ball A and ball B from the instant ball A is dropped until the time it reaches the ground. What are you supposed to draw? Position time graphs. So that's what the examiner wants. So they want position time graphs to show the motions of pole A, of both pole A and pole B, from the instant pole A is dropped until the time it reaches the ground. Take the ground as the zero position. Label the graphs A and B. Clearly indicate the following on the graphs: the starting time for each ball, the initial position, right, for each ball, of each ball. Okay, let's see. The time taken when the balls strike the ground. Okay, so let's just see that. Solution. Solution. Right, on the same system of axes, draw position time graphs to show the motions of ball A and ball B from the instant ball A is dropped until the time it reaches the ground. Take the ground as the zero position. Let's look at these and how we can draw these here. On the same system of axes, position versus time graph for both ball A and ball B. Let's see that one, 3.3. Right, we're looking at the solution to 3.3 right now. Right, if we're looking at upwards as positive. So upwards is positive. Okay, let's see what we can draw. Vertical axis, horizontal axis like this. Time. Position M. Right. So continue. Right, so now in drawing these, what do we then say here? What do we then say here to these things? So we just continue, please, quickly. Right, so we just need to sketch the graphs now, and I shall sketch them just with ease. It's painless to do that. Okay, after this, then I'm going to give you an exercise from another past exam paper so that you can just use these skills. Right, so let's look at pole A, because pole A was dropped from the top of the building. Then its position versus time graph, how does it look like? After how long did A hit the ground? So, right, it was dropped from 15.2 meters. And then its position started decreasing because it was getting closer and closer to the ground. Right, it started getting closer and closer to the ground. So its position was decreasing. And you understand, therefore, that according to the calculation we made, A was able to hit the ground after 1.76 seconds. And then ball B was thrown up. from the ground. So when ball B was thrown up from the ground, it went straight up and then down. 0.81. So B went up and then was able to hit the ground after 1.76 seconds, but it was ball B was thrown up 0.81 seconds when after A was already in flight and going straight down. So B was just thrown and did this. Okay. Because it went up and then down. So this is sort of what happened with ball B. But when A was thrown, its position started decreasing. But when its position started decreasing, it decreased with time. It changed with time like that. Right, so I want us to look at this carefully and try to make sense of this. Because we already said delta y is vi delta t plus 1/2 a delta t squared, like this. Okay, let's look at the relationship between position and time here. 1/2 a delta t squared. Okay, the relationship between position and time, what is it? Right, the relationship between position and time is the highest power of time is 2, and therefore it's quadratic. Therefore, that is why here, when position and time are related, you have a tendency of these parabolic. So this sort of resembles a parabola, because the parabola graphs either it's this or that. Okay, at least for this form. But now they can also be this way, and they can also be that way. Okay, yeah, but these are not popular in the curriculum. But the most popular are the ones facing up or down. Right. So this is sort of what we can obviously understand here from this question. But it's when we're choosing upwards as positive, but also you can choose downwards as positive. Let's look at that. 3.3. Downwards. As positive. So the time so you have 0.81 that for B. Right. So because downwards is positive, then we understand that B went up and therefore its position was like negative. Okay, this is like displacement, which was negative. Not distance, this position is displacement. Then we understand therefore that when A was released, it was released downwards, and therefore when A was released downwards, we chose upwards as positive, and therefore downwards is negative. Downwards is negative. So we have B and then A. Right, so this is what we have. here. Now, okay, so A was okay, 0.81. A was released from this position, from that height, and following a parabolic path because of the change in this. Change in y is vi delta t plus half a delta t squared. So there was a sudden change like this in the position relative to time, but the relationship is parabolic because of the quadratic 2 in time. So that's why it follows this sort of path here. And then now when B was thrown up, and we're taking downwards as positive, and therefore it went up. When it went up, then we're considering the position as therefore negative. Okay. And therefore it went up and its position was therefore negative. And we understand therefore that its position as it went up, it sort of increased in the negative direction and further reduced that way. And further reduced that way. Right, so we understand therefore that B was thrown up and then came down. So when it was thrown up and then it came down, whereas A was just, this was B, whereas A was just released and it went straight down. But again, when it goes straight down, as I said, the position varies parabolically. So it becomes sort of a parabolic shape here. Now, the couple of things, obviously, one needs to sort of consider in this case. What is it that one needs to consider? Because if you take upwards as positive, the acceleration, for instance, that is down becomes negative. Okay. Right, I want us to analyze this very, very carefully. Because if you take downwards as positive, that would mean that A is 9.8, that's what I mean here, meters per second squared. Okay, that would mean that the acceleration is 9.8 meters per second squared, meaning the acceleration is also positive because it's downwards. Okay. Right, so, and when that happens, for the position versus time graph, let's analyze what happens here. So you'd have VI delta T 1/2 9.8 delta T squared. Okay, I'm going to send you another question for you to practice here. But now this is VI delta T plus 4.9 delta T squared. So we have that. So in the end, what then happens is, okay, you'd have a positive 4.9 here, and if it's positive, the quadratic, how does it look like? So obviously, if it's positive, then it's going to be like this. So that's why sort of this shape is like that. That's why this shape is this way of the parabola there, in particular for both the A and the B. Okay, think of these shapes and make sure you can really make sense of these. Make sure you can make sense of these shapes. All right. Yeah, let's just take a break now. I'm going to send you another question on projectile motion, vertical projectile motion, and then you're gonna send me feedback. I'm just gonna pick one past exam paper and send to you so that you can try to make sense of these things and send back to me. Then I'm gonna mark and we'll talk. Okay.
Okay.
Yeah. Okay. So thanks for now, Lerato, and goodbye for now. I'll send it now.
Okay.
All
All
right.
right.
Thanks,
Thanks,
Lerato.
Sasha.
Goodbye.
Bye.
Goodbye.